All right, what's up, guys? In tonight's video, we're going to pick up with some multivariable calculus, and today we're going to be talking about evaluating some double integrals. So I have about 5 examples of iterated double integrals. Well, actually 4 examples of some iterated double integrals. So basically, an iterated double integral is an integral that's already set up. We don't have to set it up. We just need to go through and evaluate the integral. And then we have a double integral for the last example. That is one that we need to set up given the following region R. So as I've said in previous videos, the hardest part of double integration and triple integration for me is actually setting the integral up as an iterated integral, because in most cases for a double integral, you'll be asked to integrate over some region, generally a rectangular region or a general region. You may need to, in certain cases, do a change of variables and evaluate an integral in polar coordinates or a double integral in polar coordinates. And pretty much the same thing for the triples. What's hard about those is, again, to me, actually setting them up. Evaluating a double integral is not as hard as people think it is, because essentially what you're doing is you're basically dealing with each integral one at a time with respect to whatever variable you're dealing with first. So it's actually not that bad. To me, setting up a double integral and a triple integral is actually the hardest part of it, in my opinion. But I do have some videos on those. Again, I do not stream from Facebook often at all. If you would like to see my mathematics review videos, I primarily stream from Instagram. So please check out my Instagram page. That's where all my math content is going to be posted. But today, or tonight rather, I'm going to go ahead and just stream from here. I'm going to run through some double integral problems and just show you guys how to just evaluate some of these. And then we got one at the end where we actually have to set it up given the region R. So if you got any questions, you just let me know. Hopefully you guys can hear and see me very well. We're going to get started. And we got about 5 examples we're going to go through. So this is an extended video, but they shouldn't be too difficult and shouldn't be too long of a process. All right, so we're going to start with the first iterated integral. It's already set up for us. We just have to go through and evaluate it. So you get this double integral here from negative power 4 to positive power 4. We got from sine of x to cosine of x, and we got dy dx. So for the double integrals, it's kind of like a partial derivative, because in this particular case, notice how we have dy dx. What that tells me is we're going to integrate respect to y first, and it's kind of like a partial derivative. We're going to treat the other variables as constant. And then once we integrate respect to y first, then we'll integrate respect to x. And it basically extends in terms of procedure to triple integrals as well. Triple integrals are done that way as well. You know, you integrate with respect to whatever variable comes first. In this particular case, it's y. It doesn't always have to be y. It can be dx, dy. We are integrating over rectangular regions. You'll learn about something known as Fubini's theorem, which is where you can actually set up an iterated double integral and evaluate it in 2 possible orders and still get the same answer. So it doesn't always have to be dy dx, and in some cases you may need to do a change of variables to evaluate an integral in a different coordinate system. So we'll start with this double integral here. So what you do for the double integrals is we start from this innermost integral and work our way to the outermost one, and we'll begin by integrating with respect to y. So what that means is we'll have the integral from sine of x all the way up to cosine of x. And again, this is a double integral, so we're integrating with respect to y first. Okay, so since we're integrating with respect to y, and we just have dy, well, that just means that if we integrate that, we'll just get y. And then we just need to evaluate that from sine of x all the way up to cosine of x. And then the fundamental theorem of calculus, part 2 of the fundamental theorem of calculus, says that we have f of b minus f of a. That extends to double integration. There is no difference. So the upper limit gets subbed in first, and then we sub in the lower one. So if we sub in the upper limit, this one obviously is very easy. We just get cosine of x minus sine of x. So believe it or not, we've taken care of the first variable. Now we move on to the outer one. That's the whole concept of the double integrals. It's actually not that bad. Double integrals are not that bad. Triple integrals are not that bad either. In terms of evaluating them, it's actually setting them up that's actually the hardest part of it, in my opinion. So now we got the integral this time from negative pi over 4 to positive pi over 4. And this time we got cosine of x minus sine of x. And we're going to be integrating this now with respect to x, since we already went ahead and took care of the y's. So you can break this up using the difference rule for integrals. So this is actually the integral from negative pi over 4. And by the way I'm doing it here is a rather long, drawn out way of doing it. For double integration, by the time you get the multivariable calculus, you're going to be pretty good with integration by that point, and you're going to fly through most of this quite quickly. But for the purposes of the video, I'm just going through every small, minute step of how to do this. So don't assume that because it's taking me this long, that it's going to take you that long. I'm just trying to teach you guys how to do it. So that's why it's taking some time to get through it. So don't assume that it's going to take you this long, because it probably won't. And if we use the if we use the difference rule here, it applies for double integrals as well. This is really what the integral becomes. This is why I encourage you to practice on your own, so that you can be able to do double integrals quite quickly. So let's deal with the first one. So we got the integral from negative pi over 4 to positive pi over 4. And we got cosine of x dx. All we got to do is just take the antiderivative and evaluate that from negative pi over 4, positive pi over 4. So what's the antiderivative of positive cosine of x? Well, it's positive sine of x. And that's just evaluated from negative pi over 4. Oh, I'm sorry. Pi over 4, not pi over 2. To positive pi over 4. Again, fundamental theorem of calculus applies here. Remember, sine of pi over 4, that's square root of 2 over 2. And negative pi over 4 would just basically be the same thing, except it would be negative. So therefore, it's minus negative square root of 2 over 2. Two negatives make a positive, so this is essentially the square root of 2 over 2 plus the square root of 2 over 2. Remember, the square root of 2 over 2 plus the square root of 2 over 2 is just the square root of 2. So that's what we'll get for that part. And then for this next one, notice that we have the integral from negative pi over 4 to positive pi over 4. And we got sine of x dx. Now, what you should realize here, that this is an odd function. So therefore, this is 0. Now, how do I know that? How do I know that this is an odd function? So remember, let's try it. So for an odd function, remember, all we have to do is substitute in negative x. So remember, f of negative x. If we plug in a negative x there, what will we get? So for f of negative x, let's say we subbed it in, so we get sine of negative x. Well, that just gives us negative sine of x. Now we know if a function f is odd, if f of negative x is equal to negative f of x, which is essentially what we have here, which basically means that the graph will be basically symmetric about the origin. And in this particular case, we can see that we get that situation. So basically, if you have a function that is odd and the limits are the same, but they're basically different values, in this particular case, from negative pi over 4 to positive pi over 4, if the function is odd, then that means that the integral is just 0. So in this case, it's just 0. So in this case, all we really have here is the square root of 2 minus 0, which is just the square root of 2. So therefore, the final answer for this double integral, which you'll write here, is just going to be the square root of 2. So make sure you go back and review your properties of definite integrals, even in odd functions and things of that nature. So this is our final answer. We're going to move to the next one. This one was actually pretty easy. Again, like I said, these double integrals are actually not that bad, despite how they may look. Notice how we just broke everything up. So the answer to this first one, just square root of 2. That's the answer to the first double integral. So we'll circle that one with a red marker here. And we'll move on to number 2. Most double integrals, again, you're going to have to set them up. But I have videos showing you guys how to integrate over rectangular regions using Fabini's theorem, general regions, polar integrals, triple integrals. I got videos in spherical coordinates for triple integrals, line integrals, surface integrals, all kinds of stuff, volume integrals. So I got videos on that. But again, I don't stream from Facebook routinely, so please check out my Instagram page for future examples. Okay, so we're on the number 2 here. And it's always good to have some colorful, like pens or markers or something like that, just in case you want to mark around, just if you want to practice on your own. Okay, so what about this one here? All right, so same process that we applied to the first one here. Again, we have this double integral, and it's an iterated integral. It's set up for us. All we need to do is just evaluate it. Iterated means it's already set up. It's going to be from 1 to 4, from 0 to 4. We got the square root of xy dx dy. So the first thing that we need to do here is we actually need to split this up. And the reason why we need to do this is because we know for the double integration, we're going to be integrating with respect to x first, and then we'll need to integrate with respect to y. So we're going to have to break this up. So keep in mind that if we use some algebra here, we know that the square root of xy, that's the same thing as the square root of x multiplied by the square root of y. It's the exact same thing. And the reason why we need to break that up is because we have to do the double integration this way. So actually, we can simply rewrite the integral as the double integral from 1 to 4. From 0 to 4, and just simply rewrite it as the square root of x times the square root of y dx dy. It's the exact same thing as that. All we did was just use some algebra. That's all. Use some properties of square roots. Now that works out perfectly because we know we have to integrate with respect to x first. So since we're integrating with respect to x first, remember, it's kind of like a partial derivative. We're treating y as a constant. That means we can bring square root of y outside. And then we're going to be integrating from the innermost integral here to the outermost one. So the square root of y just comes out. It's a constant, remember. And then we're evaluating that from 0 to 4. Or multiplying, we apply the constant multiple rule. And then we'll have the square root of x dx in here. So if we apply the constant multiple rule, we know the square root of y just comes on the outside. Remember that the antiderivative of the square root of x is just 2 over 3 x raised to the 3 over 2. That's just something you kind of got to remember. How do I know that? Well, again, remember that the square root of x can be rewritten as x raised to the 1/2. So rewrite the square root of x as x raised to the 1/2, apply the power rule for integrals, and you should end up with that. So that's how you get 2 over 3 x raised to 3 over 2 if you don't know how. And then that's going to be evaluated from 0 to 4. Okay. And it's always good to have your calculator as well. I don't know where mine is. It's right here, just in case you may need it. Numbers aren't getting too big here, so we shouldn't need it, but I have it near me. And we sub in the 4 first, and then we sub in the 0. Clearly, we already know what we're going to get when we sub in the 0, so we know we're just going to get 0. So really, we're just going to get the value for whatever we get when we plug in the 4. So we sub in the 4 for the x part here. Make sure you take care of the exponent stuff first. Again, use your PEMDAS rules. A lot of students forget about those PEMDAS rules that we learned about in school. And they try to do things out of order, and they end up getting the wrong answer. So make sure you're using your order of operations. Those are still valid. So 4 raised to 3 over 2 times 2 over 3, that's just going to be 16 over 3. We know that if we sub in the 0, we're going to get 0. So we're just going to end up with that plain old 16 over 3. Now, if we multiply that by the square root of y, again, 16 over 3 is just a constant. But we're going to need to integrate with respect to y. So essentially, we could just take the 16 over 3 out if you want to. We would just apply the constant multiple rules, and it really doesn't make that much of a difference. And then we'll just integrate the square root of y, which is basically the same thing as this, except we'll change it from an x to a y. So now for the outermost integral, again, what we have is the 16 over 3 is just a constant. And now we're moving to our outermost integral, and it's going to be from 1 to 4. And this time, we're going to be integrating that square root of y with respect to y. Now, we already know what the answer is to this because we're going to get 16 over 3 if we apply the constant multiple rule. And we already know what the antiderivative to that is because we know what it is up here. It's just going to be 2 over 3, y raised to 3 over 2. Again, that's just something you kind of got to remember. But you can always use a little bit of algebra to rewrite the integrand such that it's easier. Again, we already know what the answer is going to be here for this. We know that if we sub in the 4, we'll get 16 over 3. Now, if we sub in the 1, that's even easier because essentially 1 raised to whatever in this particular case, and then it's going to be times 2 over 3, which is going to give us 2/3, right? So we're going to have minus 2 over 3 because that's what the fundamental theorem of calculus says. It says that we're going to have f of b minus f of a. Now remember, to subtract fractions, we need common denominators, which we have here, so that's perfect. So this just simply gives us 14 over 3. Now we need to multiply this constant out here, the 16 over 3, by this 14 over 3, and end up getting our answer. So 16 over 3, we need to multiply that by 14 over 3. Okay. Now, there's a really, really cool way to do multiplication of numbers like this and actually be able to get the answer. I know that 6 times 4 is 24, so I guarantee you that 16 times 14 is 224. And I know that 3 times 3 is also 9. That's a really cool multiplication trick. I'm going to have to show you in another video how to do that. But we'll actually check it just to make sure. And I encourage you to do this. A lot of students will not take the opportunity. Yep, 224. I'm going to show you guys a really cool math trick, how to get the answer to stuff like that. And you also need to make sure you can simplify it as well. I don't believe you can break this down any further. It's good to have a calculator. And make sure you use your calculator to check and see if your arithmetic is correct. I mean, we really can't do anything with that. So our answer here is just going to be 224 over 9. So the final answer for this one, some students won't take their calculator and they won't go through and actually check their answer to make sure it's right. And in actuality, they went through the integration process quite easily, or not quite easily, but they went through it, correctly, but they didn't take the second to just go back and check their arithmetic. I remember I was doing a math test at one point, and it was like a triple integral, and I was doing it, and I was working so hard on the triple integral that my arithmetic is actually what got me the wrong answer. Now, I know that 3 cubed is 27, but I was going so fast and working so fast through that triple integral that I wrote 3 cubed is 9. So I ended up getting the whole thing wrong. And I get the test back from my professor, and I'm flipping about why I got wrong, and just me not being lazy and not wanting to take a few minutes to go back and check my arithmetic. Nobody's perfect but God, so you're gonna make mistakes. So please don't give professors an opportunity to take points away from you. Math tests and quizzes, passing or failing a math quiz sometimes only comes down to a couple points, and you don't want the couple points to go away just because you didn't want to take time to go back and check your answers. So that's the answer to the second double integral. So we're going to try another one. We got 5 of them, but again, we're running through them quite quickly without any issues. All right. Again, let's make sure that you check out my Instagram page for the streaming of these. That's where I primarily stream these from. Let's make a little bit more room. All right, what about this one? All right, so don't let this one scare you away either. We're going to apply the same principles here. We do got some odd variables here. We got t, and s or whatever. But again, it doesn't make a difference which variables are being used. The process it's the same. So clearly here, we're going to be integrating with respect to s first. That means we're treating t as a constant. And the limits here are the same for both integrals. So since we're integrating with respect to s first, that means that t squared can come out. And we'll multiply that by the integral from 0 to 1. Now here we got e to the st. I understand that the t is a part of this exponential, but you can't strip that away. It's an exponential, so you have to leave it that way. So it's e to the st, and you're going to be integrating that with respect to s. So you can't pull the t out. I know that there's a t in it, but you can't pull it out. It's part of that exponential. So hopefully you guys know the answer to this. Obviously, the exponentials are easy to integrate, but let's just say, for example, you don't know how to integrate this. How will we deal with it? Well, you can do a u substitution, but you do have to be a little careful here. Now, clearly, the option for u here is pretty simple. It's just going to be st. Now, keep in mind, we're integrating with respect to s. And in this particular case, we're going to be differentiating pretty much with respect to s as well. So you have to make sure that you pay attention to that. That's the only kind of confusing part of this. So if we differentiate this, we're just going to get t ds. And so then we'll end up with du over t is equal to ds if we actually solve for the ds part. Now, essentially what you could do is you got your t squared, which was there. Du over t, I could pull out a 1 over t and just leave the du in there. So that'd be 1 over t. Okay. And then we got the integral, and again, since this is a definite integral and we are changing the limit, doing a u substitution, we do have to change the limits, but we just got the e to the u du on the inside here. Let's just go ahead and change the limits, okay? It's very easy to change the limits here, obviously. So u is just st, so all we would have to do is just sub in the 0, sub in the t, and so the new limits here are just going to be from 0 to t. Again, this is the long way to do it. By the time you get to multivariable, this stuff would be quite easy for you. You won't have to do all these small little steps. So you can simplify the constants on the outside first if you want to. It's perfectly fine. T squared times 1 over t, that's just t. If we take the antiderivative exponential e to the u du, that's just e to the u, just get itself. And then we evaluate it from 0 to t, basically. Apply the fundamental theorem of calculus. Same thing. So we just get e to the t. E to the t. Remember, e to the 0 is 1, so that's going to be minus 1. So now we got t times all of this, and now we need to evaluate that from 0 to 1. So now, for our innermost or our outermost integral now, we have from 0 to 1, and we got t multiplied by e to the t minus 1, and now we're integrating all of this with respect to t. So how do you deal with this one? All right, so key word of advice here. Before you think, okay, I'm going to distribute the t, keep in mind that if you distribute the t, you're going to have to apply integration by parts regardless. If we're going to actually evaluate this integral here, we need to apply integration by parts. Now, let's just say we go about distributing the t, because I think that's what some students would probably try to do. Then this is essentially what you'll have. You have the integral from 0 to 1, and if you distribute the t, it looks like you'll have t times e to the t minus t dt. Understand that to evaluate this integral, I still have to apply integration by parts, because I could break this up with the integration sum rule, or actually the difference rule, since the minus there. And if I'm integrating from 0 to 1, t times e to the t, I have a product of two different functions. So you distributing the t in doesn't stop you from having to use the method integration by parts. You're still going to have to use the method because we still have a product of functions here. So the best thing to do here is to just do the integration by parts. Distributing the t is not going to make any difference. So just start off by doing the integration by parts. And we have to do that here. We have a product of two different functions. So remember the integration by parts formula, which is just derived from the product rule for first semester calculus. I'll just abbreviate the integration by parts with P apostrophe S. Remember the formula for that? That's just the integral of u dv is equal to uv minus the integral of v du. And you make sure you want to have that written down, or make sure you have it memorized. In order to use this technique, you have to have it memorized in order to use by parts. So make sure you have that memorized somewhere. Just integrate both sides of the product rule, and you get that guy there. So remember, for integration by parts, we identify what u is, we identify what dv is. The great thing is, once we identify what the u is, dv is everything else. In this particular case, again, neither of these functions are harder or to integrate or differentiate than the other. In this particular case, if we're going to do integration by parts, I'm just going to pick u to be t, and then that means that dv is everything else. So dv is e to the t minus 1 dt. So there's no reason to really distribute there. Just go ahead and start with the differentiation. So by parts says we need to find the du. Well, if we take the derivative of t, well, that's just 1. But if we multiply it by dt, we just get dt. So therefore, du is just dt. And then remember, to get the v part, we just integrate dv. So that's the antiderivative of e to the t minus 1 dt. Well, that's just e to the t minus t. You don't need a plus c here. We're just doing integration by parts, so we'll tackle, we don't need to tackle on a plus c. Okay, so now what we do is we take you want to take a bracket, and I highly recommend doing this when it comes to integration by parts. You want to make sure that you have stuff nice and neat. If you have stuff laying all around the paper, you're not going to probably do very well in the by parts. So try to make sure everything is neat. So remember that multiplication is commutative. So for the left-hand side, when you're doing the u times the v, you can kind of flip it around however you want to. Multiplication is commutative, so it doesn't make a difference. So you can kind of get creative with this side. But you need to make sure that you integrate the the right-hand side as well. So on this side, I'm just going to write it as t multiplied by e to the t minus t. And if we have the integral of v du, then that means we'll have minus the integral of essentially e to the t, and I'll put parentheses around it, minus t dt. I'm actually going to break it up. Okay. And again, this is going to be from 0 to 1. So let's take care of the innermost integral here. So the innermost integral here that we have is e to the t minus t dt, and that's just clearly going to be e to the t minus t squared over 2. We use the product, I keep saying product rule, we use the power rule, excuse me, for that part there. Okay, so again, once we've taken care of the integration on the inside, we can kind of clean things up a little bit. You can expand the inside if you want to. So again, we didn't really touch this side. Again, multiplication is commutative, so we got e to the t minus t. And then we'll have minus the integral of v du, so that means we'll have minus all of that, which is e to the t minus t squared over 2. and that's evaluated from 0 to 1. Now you can sub in the 0 and the 1 that way if you want to and just kind of go with it, or you can kind of clean this up a little bit. Notice that this is t squared over 2, so I can actually distribute this t and actually expand out and bring out a 1/2 to make things a little bit easier, because we know that e to the 1 is just e, and we know that e to the 0 is 1, so that'll make things a lot easier. So I'm going to expand the inside here, so let me get another sheet so we can do that. So I'm going to expand the inside and pull out a 1/2. That will make things a lot easier to deal with. So if we do that, we'll have 1/2. And then if we expand this out, we have to be careful with the signs. All right, so it looks like we'll have negative t squared. Let's see, this would be plus, I don't know, plus 2 e to the t multiplied by t. Make sure I'm pulling everything out correctly. And that's going to be minus 2e to the t. Just use a little bit of algebra to kind of clean that up. And it's going to be from 0 to 1. And you want to do that because, again, we know that e to the 1 is e and e to the 0 is 1. So it'll be easier to evaluate this way. All right. So now, essentially what we have is you, again, apply the fundamental theorem of calculus. You plug in the upper limit first, and you plug in the lower limit. So what this does for us, since we know that e to the 0 is 1, and we know, e to the first power is just e, we know that we're just going to end up getting negative 1/2 when we sub in the 1. And subbing in the 0 would just give us a negative 1. So we'll have negative 1/2 minus negative 1, which is essentially just negative 1/2 plus 1, which we know is positive 1/2. So that's actually going to be our answer. So the final answer for this not triple integral, I'm sorry. I'm going to do a video on triple integrals. This is a double integral, but final answer for this double integral, which was the integral from 0 to 1, And I'll post pictures of the solutions for this so you don't have to watch the entire video in order to get the solution. If you don't want to watch it, you can just take a look at the solution. So the final answer for this is just positive 1/2. So that's number 3. So we're actually moving through these quite quickly. And I believe in giving a very detailed explanation of everything that's going on. That's why my math videos take a bit of time. I don't leave anything out. In a multivariable calc class, your professor's going to assume you know how to do most of this stuff, and they're probably going to fly through it and not explain very much of it. So if you kind of got lost in Calc 2 and you really didn't pick up on the stuff that you needed to pick up on, they're not going to be nice about it. So in my videos, you get more bang for your buck because I go through everything. All right, so we're on the number 4. And again, this one looks hard, but it doesn't take long at all. And we got one more after that, and we'll pretty much be done. So I'd say about another 10 minutes or so for this one video. It's an extended one. Same thing here. So you got this double integral from 1 to 2 from 0 to ln of x. We got x cubed times e to the y dy dx. So again, we know that since we're integrating respect to y first in this case, and notice how it's respect to y first, it wasn't x like it was for the last problem that we just did. Sometimes it won't be respect to x, it could be. And again, when you can watch some of my videos on my Instagram page where I talk about integrating over rectangular regions. We use something known as Subini's theorem, which I've talked about before. We'll talk about that in another video. But what I'm going to do is I'm going to pull out the x to the third because we're integrating respect to y first. So I just take that out. And it's going to be the integral from 0 to ln of x. And then we just simply have e to the y dy in there. Okay, well, we just get x cubed. Sorry. We get x cubed. Take the antiderivative. We just get the e to the y, basically. This is evaluated from 0 to ln of x. Now, we know that the exponential and the log function or the exponential and the logarithmic function are inverses of each other. So e raised to the ln of x is just x. And then we know that e to the 0 is 1. So that's going to be x minus 1, basically. And so then we just multiply by x to the third and then evaluate from 1 to 2. So now we're moving on to the second integral now. So as you can see, it's actually not that bad. All double integrals won't be this easy. I have some really, really complicated ones that we can work on, maybe in another video. So if you want to see ones that are a little bit more challenging, we can certainly do that. But in this video, we didn't want to go too challenging, although the one that we did before this one maybe was a little bit involved. So again, here, notice we can just distribute here, and it's not going to require by parts or anything like that. So yes, you can distribute here if you want to and break this integral up. So this is just going to be from 1 to 2. And if you break this up using the basically the difference rule for integrals, this should just be x to the 4th dx minus the integral from 1 to 2. And this should just be x to the 3rd dx. So again, these are small little steps that you guys will fly through this quite quickly by the time you get to Calc 3, which is when you start learning about this stuff. So you'll be fine. Don't worry, it won't take this long. So we apply the power rule. That's x to the 5th over 5. And that's going to be from 1 to 2. And you basically sub the stuff in. And so you get your calculator and you make sure you have that and you sub it in when you need to. So remember that 2 to the 5th. And again, notice how I'm plugging everything in. That's 32 over 5. We know that if we sub in the 1, we'll just get 1 over 5. So make sure you sub in everything correctly. And so this is just essentially 31 over 5 for that part. And then for that last part there, the integral, again, it's just a long way. You don't have to do it this way. It's x to the 3rd. Well, you have to do it this way, but you don't have to write out all the steps. I won't say you can't. You don't have to do it this way. This is the actual way you do it, but it's the long way to do it. So you just get x to the 4th over 4, and basically the same process. It's just going to be from 1 to 2, and you just sub in the appropriate information, and you see what you get. Now, we know that 2 to the 4th is 16 because we know 2 to the 3rd is 8. So if we divide 16 by 4, we get 4. So it's going to be 4 minus 1 over 4. 4 minus 1 over 4, that's 15 over 4. And again, remember, anytime you want to subtract a whole number from a fraction, again, a lot of times you can do it in your head, but you can always check your calculator to look at it. But what you need is you need to get a denominator that's common with this one down here in order to subtract them. Because remember, in order to subtract fractions, we need common denominator. Same thing if we add them. But that's going to be 15 over 4. Now notice how I'm going to go into my calculator and I'm going to check. I always tell my students, it does not make you a bad math student to go back and check your answers. So 15 over 4 doesn't make you a bad math student at all. Makes you a great math student to take your calculator and say, hey, let me go back and just check and make sure my arithmetic is correct. So now we got 31 over 5, and we subtract that from 15 over 4. And again, we need common denominators to subtract fractions, but just to kill time, just use a calculator. It's just that simple. So here we got 31 over 5 minus 15 over 4. And we get 2.45, and then so all you have to do is just kind of go here to the math section. You click on the fraction. If you don't know how to do this, it may be different for different TI. I have TI 84 plus, but you just click on the fraction part, and it just converts that decimal to a fraction for you, which is just 49 over 20. And so that'd actually be the answer for this one. And that's the answer to number 4. And we got one more, and that's it. We're gonna be done after that. So that's the final answer for number 4. And believe it or not, triple integration, again, the hardest part of triple integration, much like for double integration, actually setting the problem up, not actually going through the triple integral. I'm going to do a video with the triple integrals as well. I'm going to do a video with line integrals, surface integrals, volume integrals, all of the stuff you learn about in vector calculus. And I got material on vector calculus all on my Instagram page, so check that out. You know, divergence, curl of a vector field, all that good stuff. Especially for me, since I studied physics, I have a physics degree, I really needed to understand stuff like vector calculus in order to understand Maxwell's equations and the Schrodinger equation and all that kind of stuff. So the answer to this is 49 over 20. So that's the answer to number 4. And we got one more, and then we're going to be done. I'm going to let you guys go. All right, let's do this last one, and we will be good. Where did I put it? All right, so this one is one that we need to set up. I wanted to do one like this because I thought it would be very cool. I need to make some room. So like that. Okay, so we have this double integral here, and notice how it's not an iterated one that's already set up for us. Most double integrals are going to be given like this. They're going to give you some region, and you need to set it up yourself. So I do have some videos on this on my Instagram page, so please check that out. How you set it up depends on the region that you're integrating over. In most cases, but in this case, we just need to set up the iterated integral. So they give us the region R here, and we just need to set this up. So it's very simple. I want that to fall. So it's very simple to set this up. So we got this double integral. Again, R represents the region. And we got 6y multiplied by the square root of x minus 2y cubed dA. Now notice that the dA part here, in this particular case, the dA part is just going to be dx dy. So if we set this integral up, this is just going to be the double integral, and all you got to do is set it up. Now you have to make sure that the variables correspond, your limits correspond to the correct variable. That's the hardest part of the double integration, and I was talking about that with the triple integration, is setting it up. Sometimes you'll set it up incorrectly, and that's what gets students. That happens a lot with Fubini's theorem, which basically says that you can do it two different ways. You can integrate it dx dy, dx for Fubini's theorem, which is where you're integrating over rectangular regions. But sometimes what students will do is when they go to integrate it the other order, sure, they'll switch the dx to dy, but they won't switch the integrals. And so they'll keep the same limits for the same integrals and end up getting the wrong answer. So this is just going to be from 0 to 3, and then this is going to be from 1 to 4. If we're setting it up correctly, make sure you're doing that. And then we just have what we had in there anyway, which is just 6y times the square root of x minus 2y cubed. And then remember the dA part is just a dx dy. All right, so you're probably like, okay, Krishan, what the heck do we do here? Well, we apply the same process that we applied to the previous examples that we went ahead and take care of. Let's do no different here. So we know we're going to start integrating from 1 to 4 first. So I always say just set it up kind of like this first if you're practicing on your own, just to kind of get you in the mindset of how kind of this thing kind of works. Okay, and then start removing stuff like that. So since we know we're integrating with respect to x, that means that we're treating y as a constant. So what that means is that if we want to, we can actually apply actually, let's do it that way, because I think it might be a little better to maybe do it that way. Let's apply the difference rule, very similar to how we did for the first one. So we got the integral from 1 to 4. In this particular case, let's just break it up. So we get 6y times the square root of x dx. It might be easier just to see what's going on this way instead of doing it the way that I was going to do it a few seconds ago. We got 2y cubed dx. Yeah, this is probably a better way to do it. Okay, so let's deal with the first one. So from 1 to 4, we got 6y times the square root of x dx. So again, since we're integrating with respect to x first, that means that the 6y is, not only is the 6 a constant, but the y also is. So that can just come out. What's the antiderivative of the square root of x? Well, remember, we talked about that. It wasn't the example that we did previous to this, but it might have been the example before that. Remember, that was just 2 over 3, x raised to 3 over 2. Remember, that's just something you kind of got to remember, or just simply rewrite the square root of x as x raised to the 1/2 and apply the power rule, and you should get that. And then that's evaluated from 1 to 4. Okay. Now we already know what this is going to give. We're going to get 16 over 3. Actually, and we know it's going to be minus basically 2 over 3. Which again gives us 14 over 3. Then we multiply that by 6y. So you got 6y multiplied by 14 over 3. 6 times 14, I think that's 84. I'm going to check. 6 times 14. Yeah, it's 84. Now, if we divide that by 3, so we got 84y, and we divide that by 3. And you always want to make sure you simplify as much as possible. That 84y is in the numerator, by the way. And 84, I think that's going to be 28. Yes, 28. So we get 28y. That's what we get when we break up the first part. Again, this is very confusing since I'm doing it in small little steps like this. That's why I encourage you to do multiple practice problems so you don't have to do it in small little steps like this. But this is a good way to learn how to do it for the first time. So that's what we get. So you're going to have to keep track if you're doing it this slow way, kind of like I'm doing it. You'll need to keep track of where you're at. All right, so let's take care of the next one. So from 1 to 4, we got 2y cubed dx. And another reason why I do it this way is I don't want to fly through something and then you guys get lost. I don't like it when teachers do that. You just fly through stuff and you have no idea where the heck they got the answer from. And that's probably because they're assuming that you already know it or should know it. And in my videos, a whole bunch of people watch. Not just there's some people that don't know anything about math at all. That just like to watch the videos, which I don't mind. And they don't know how to integrate. You know, everybody doesn't know calculus. Some people just like to show support in the videos, which I appreciate. By the way, thank you for the support. All right, so we're going to take care of this part. So from 1 to 4, we got 2y cubed dx. So again, not only is the 2 a constant, but the y also is a constant. So that means we have to treat it that way. So since we're integrating with respect to x, this is actually just 2y cubed multiplied by x. And that's evaluated from 1 to 4, since we're treating that other variable as a constant. Same process here. Apply the, fundamental theorem of calculus. So here, we just simply get 8y cubed minus 2y cubed, which obviously is 6y cubed. So now, when we move on to our outermost integral now, which will be from 0 to 3, we know exactly what we're going to be integrating. So from 0 to 3, we're going to be integrating basically 28y minus 6y cubed. And this time, we're integrating with respect to y. So look, we're almost done. Just that simple. Some people are like, oh man, double integration. You just got to practice. Practice doesn't make you perfect. Nobody's perfect but God. So don't assume that practice will make you perfect, because it won't. And I'm just breaking this up with the difference rule. And contrary to popular belief, I know a lot of people think that I just automatically just woke up one day and just understood this stuff, and that's just not the case. It took a lot of work, a lot of practice, a lot of dedication, a lot of 2 o'clock, 3 o'clock in the morning working on differential equations, just doing a bunch of practice problems. That's how I mastered this stuff. I didn't just wake up one day and understand this stuff. It took a lot of practice. And it's going to take the same thing with you. Okay, so let's just go through the last 2 parts. Again, I'm just breaking it up, just trying to apply some enthusiasm. And the great thing about math is that once you actually learn how to do this stuff, you actually find yourself having a lot of fun actually doing it. I have so much fun doing these videos because I actually understand what the heck I'm actually doing. So it's so easy. It's so much better for me if I know what I'm doing. So all I did here in this particular case, I took the 28 out. It's a constant. Again, you could be able to go through this process quite quickly by the time you get to Calc 3. So this just becomes y squared over 2. Again, that power rule. If you don't remember the power rule, I'm assuming everybody knows it, but let's just say you don't. Remember, if I have the integral of x raised to the n dx, that's just x raised to the n plus 1 all over n plus 1. But there's a restriction on this. N cannot equal -1 because -1 plus 1 is 0, and we can't have division by 0. That's a big no-no, right? So make sure that you keep in mind of that restriction. Just wanted to point that out. Sorry. And so now we just, basically go ahead and apply our limits here. So this is going to be from 0 to 3. So this gives me 9 over 2 minus 0. It's just 9 over 2. And now we get, ignore that part. Now we get 28 times 9 over 2. I don't know 28 times 9 off the top of my head. Not even going to lie. So we get 252, and I know I can divide that by 2 and get 126. So this would be 126. I'm going to show you guys that multiplication trick. I really want you guys to see how to do that. That'll be really cool for you guys to see. And then the last part was this part here, which was the integral. I know I'm got all over the paper, but I'm kind of having a lot of fun with this. So you get 6y cubed dy. So let's just tackle it the same way. So the 6 comes out. That's y to the 4th over 4. And the same thing from 0 to 3. Remember, 3 to the 4th, that's 81. Hopefully you guys remember that. So it's 81 over 4, which we can't really do anything with that. And obviously 7 and 0 just gives us 0, so we get 81 over 4. And so to finish this up, I'm almost out of paper. I have to go to Family Dollar tomorrow. Okay, so we got 81 over. And by the way, the paper that you see here, I use marker. I use Sharpie on my paper, so it bleeds to the paper. But when I was using pen, people, I can't see it. So, all right. So we got 6 times, what was it? 81 over 4. Same process that we've applied multiple times. So again, take my calculator, see what we get. So I got 6 times 81 over 4. Actually, I can simplify that in my head, quite frankly. That's going to be 243 over 2, because I can actually drop, I can do the 6 and the 4 and change that down. But we get 243 over 2. That's what I get in my calculator. If you're actually doing that with me, hopefully you get 243 over 2. So now to get the final answer, all we have to do is we have to take that 126. And if you're going to do it in this method, please make sure that you pay attention very closely to the sign that was attached and how you separated it. So that's why I mentioned the difference rule or the sum rule for integrals. Sometimes it can be a combination of the two, in which you call it the sum and difference rule. So make sure you pay attention. So it's actually going to be subtraction. We were subtracting when we started from y. So you have to make sure that you pay attention to the sign. That way you don't end up adding when you should have subtracted, or subtracted when you should have added. So now all we got to do to get the final answer is, I tapped the pen back up, is we can take that 126 and we subtract it from 243 all over 2. And it's just as simple as that. Take a calculator, do it. Even Einstein used a calculator, contrary to popular belief. So mine is 243 over 2. And notice that we get 4.5, which I know is 9 over 2. But just to validate that, you just simply go here to the math section, click on the fraction, and it changes it to 9 over 2. That's the answer for the integral. And that's the final answer for all of our integrals tonight. So notice how that one, we just had to set it up. Again, please check out my videos on double integrals over rectangular regions, general regions, non-rectangular regions, and triple integrals as well, for how to set these up. All those videos on Instagram. So the answer for this integral is just 9 over 2, or 4.5. That's the answer. All right, where's my marker at? Right here. So that is double integration. So just a small little introduction into it. Hopefully, if you have to take Calc 3, which physics majors got to take several semesters of calculus, and obviously math majors got to take several semesters of it. So you'll be seeing this stuff all day, and probably the most important calculus that you use in all of physics, if you really want to learn a lot of the really advanced topics, is going to be Calculus 3. Yeah, it's very important stuff to take a look at. So this was the answer to number 1. I've got the papers all kind of mixed up here, so it's going to be a lot hard to keep track. But this was number 1. This was number 2. Number 3 was the one that was a little bit more involved. I probably should have picked the easier one for that, but I did try to explain everything. That one was the one with the integration by parts. Number 4 was this one. All right, that one was pretty easy, and then that one was number 5. So I'm going to post pictures of all of these solutions, and that is multivariable calculus, and that is just a general introduction into double integrals. Let me know if you got any questions about this. I love talking about math. I love talking about physics, so just let me know what you got, and if you got any questions, I'll try to address it. But that's it. Y'all have a good night, and I'll see y'all next time.